Alright, welcome everyone to lecture number 2 of this course on adaptive control. Last time we had introduced the idea of adaptive control, and we had discussed a couple of examples where adaptive controllers are advantageous over traditional fixed gain controllers. I had also mentioned that for this course you need to have some prerequisite background in nonlinear systems, nonlinear control, or Lyapunov stability theory. Having said that, in this class I will talk about some preliminaries which will be required for you to take this course forward. However, I encourage that you can go back and read about these preliminaries on your own in more detail. So, this class I will talk about the fundamental concepts involved. Okay, so let us start with the stability of equilibrium points. So, as I mentioned, the stability notion is tightly tied to the equilibrium points of a system. So, normally there are various notions of stability that you might have heard about, for example, bounded input, bounded output stability, which talks about the stability of the system where bounded inputs result in bounded outputs. This notion of stability is tightly tied to the stability of equilibrium points, which is small perturbations about the equilibrium point result in small perturbations in the state. So, let us consider a nonlinear system x dot equals f of t comma x, where f of t comma 0 is equal to 0 for all time greater than equal to t naught. So, here as you can see, this function f is an explicit function of time, and so this is an example of a non-autonomous system. And the fact that f of t comma 0 is equal to 0 suggests that x equal to 0 is the equilibrium point. So, the idea is that you substitute the right hand side of the equation to 0, and the value of x for which this is satisfied for all time gives you the equilibrium point. So, in this case x equal to 0 comes out to be the equilibrium point. Okay. And for for simplicity, we will consider, without loss of generality, that x equal to 0 is the equilibrium point for a nonlinear system. I had mentioned in the last class that you could always do a change of variables, and even if you have a non-zero equilibrium point, you could convert that back to 0. So, this function f is piecewise continuous in t and locally Lipschitz in x. So, both these properties, they suggest that the solutions exist and are unique. So, existence and uniqueness of solutions is guaranteed if the function f is piecewise continuous in t and locally Lipschitz in x, and this domain D on which x is defined contains the origin x equal to 0. All right. So, let us look at the first definition. So, the origin x equals 0 of the system is stable if for each epsilon which is positive and initial time greater than equal to 0, there exists a positive constant delta which is dependent on epsilon and the initial time t naught, such that if the initial state at time t naught starts within a ball of radius delta, then for all future time the state trajectories lie within the ball of radius epsilon. So, this is illustrated by this diagram here, where x equal to 0 is the equilibrium point, and this system starts at some point x of t naught, which lies within this delta ball, and for all future time the state trajectories, they lie within the epsilon ball. So, this just suggests that the state trajectories lie close to the equilibrium point if the initial conditions are sufficiently close to the equilibrium point. Okay. A thing to note here is that the constant delta depends on epsilon as well as the initial time t naught. For autonomous system, that is for systems where the function f is not explicitly dependent on time t, this constant delta is only a function of epsilon. So, the task here is for each epsilon, if we can find a delta which satisfies this relation, then we say that the equilibrium point is stable. However, if this condition is not true, we say that the equilibrium point is unstable. That is, even if there exists one epsilon for which there exists no delta, such that if the initial conditions start within that delta ball, they are constrained to be within epsilon. So, even if there exists one epsilon for which this condition is violated, we say that the equilibrium point is unstable. So, an example of a stable equilibrium point that we had discussed last time as well was that of a pendulum. So, for this system, we consider the equilibrium point to be theta equal to 0 and theta dot equals 0. That is the equilibrium point that we are considering. You can see that if we perturb the system slightly from the equilibrium point, and suppose we assume that there is no friction in the system, then for all future time the pendulum keeps oscillating about the equilibrium point, and we can say that the system is stable. However, if we consider the other equilibrium point, which is vertically upward equilibrium point for the pendulum. So, here theta equals pi and theta dot equals 0. So, for this case, for any epsilon that we choose, it is not possible to find a delta such that if we start within, if the initial conditions start within some delta ball, they stay within the epsilon ball for all time. So, this is an example of an equilibrium point which is unstable. Let us take another example of a van der Pol oscillator. So, the equations of the van der Pol oscillator are given by this. It has two states x1 and x2, which are related like this. If we draw the phase portrait of the system, this is what it comes out to be. The origin is the equilibrium point, and for any state trajectory which starts with a non-zero initial condition, it will eventually converge to this limit cycle. So, if we construct an epsilon ball of radius 1 which lies within the limit cycle, then can we find a delta ball wherein my initial conditions lie such that for all future time the trajectories stay within this epsilon ball of radius 1? The answer is of course no. So, because these trajectories eventually will escape from this epsilon ball and converge to the limit cycle. So, this is an example of a system whose equilibrium point is unstable. So, you can also see that the trajectories, since they converge to the limit cycle, they always stay bounded, that is, the trajectories do not grow to infinity. However, the system is still unstable. So, there is a difference between stability and boundedness. Okay, so, the next is the origin x equals 0 of the system x dot equals f of t comma x is convergent or attractive if for all initial time t naught greater than or equal to 0, there exists a constant c which is dependent on the initial time, such that if the initial conditions start within this ball of radius c, then as t tends to infinity, x converges to 0. So, this is an example of the equilibrium point being convergent or attractive. That is, if this is the ball of radius c, and if the initial conditions start somewhere inside it, then eventually they will converge to the equilibrium point. So, note here that the property of convergence or attractiveness is different from the notion of stability, where we have to find a delta for each epsilon. Here that delta epsilon condition is not to be it is not required to hold, rather the only condition is that the state trajectories eventually converge to the equilibrium point. The second is asymptotic stability. So, the equilibrium point is said to be asymptotically stable if it is both stable and convergent, and we just discussed what stability is, and we also discussed what convergence is. So, if the equilibrium point is both stable and convergent, then the equilibrium point is said to be asymptotically stable. So, this illustrates the asymptotically stable equilibrium point, where the initial conditions start within some delta ball, and for all future time they stay within this epsilon ball. So, this has to be satisfied for all epsilon. So, if it is indeed true, we say that the equilibrium point is stable, and in addition to that we also see here that the state trajectories eventually converge to the equilibrium point. So, this equilibrium point is not just stable, but it is also convergent or attractive. So, this is also illustrated here, where you have a 3-dimensional plot of the states x 1 and x 2 and time. So, here as t goes on, the trajectories eventually converge to the equilibrium point. Okay, so, let us take another example here of a system where the equilibrium point is the origin. So, here this is a special system where if the state trajectories start from any non-initial condition, then they will reach a curve C, and then eventually they will come back to the equilibrium point. Okay. So, can we say that the system is convergent? Yes, it satisfies the definition of convergence that we just mentioned. Is this system stable? No, because if we consider this epsilon ball of radius 1, we see that any initial condition will eventually leave this ball and reach the curve C. So, we cannot constrain the state trajectories to lie arbitrarily close to the equilibrium point, even if we start very close to the equilibrium point. So, convergence in general does not imply stability. Okay, so, how about the reverse? Does stability imply convergence? So, that is also not true. A system an equilibrium point may be stable, the convergence may not hold, that is the state trajectories may not converge to the equilibrium point. So, next we go to the concept of uniform stability. So, this concept is very critical for systems which are non-autonomous, that means where the function f is explicitly dependent on time t. So, the origin x equals 0 is uniformly stable if for each epsilon greater than 0 there exists a delta which is dependent on epsilon, which is a positive constant, independent of t naught, such that if the initial conditions start within a delta ball, they stay within an epsilon ball for all future time and for all initial for all values of the initial time greater than equal to 0. So, the important thing to note here is that the delta that we have used here is independent of the initial time t naught. So, in general for non-autonomous systems, the stability behavior is also dependent on the initial time. That is, if we start the system at some initial time, it will have some stability behavior. If we start the system at some other initial time, it will have some other stability behavior. When we say that a system an equilibrium point is uniformly stable, what we mean is that the stability behavior is independent of the initial time and the equilibrium point is uniformly stable. Okay, so, the second concept here is uniformly asymptotically stable. So, an equilibrium point is uniformly asymptotically stable if it is both uniformly stable and uniformly attractive. So, we just talked about uniform stability. So, what does uniform attractiveness means? It just means that if there exists a constant a positive constant c which is independent of T naught, such that if the initial conditions start within a ball of radius c, then the state trajectories eventually converge to the equilibrium point as t tends to infinity uniformly in T naught. That is, the convergence is also uniform with respect to the initial time T naught. So, this is very important, and this is a stronger notion of stability than just saying that an equilibrium point is asymptotically stable. The fact that we can say that the equilibrium point stability behavior is independent of the initial time is a very strong notion. For autonomous system, that means systems of the form x dot equals f of x, stability and uniform stability are the same notions. Similarly, asymptotic stability and uniform asymptotic stability are the same notions, because here the solutions x of t of these systems are not explicitly dependent on the initial time t naught, and so the stability behavior is anyways independent of the initial time T naught. So, both these notions are equivalent in the case of autonomous systems. A yet stronger notion of stability is exponentially stable. So, in the uniform asymptotically stable case, this condition does not talk about the rate of convergence towards the equilibrium point. It just states that the state trajectories asymptotically converge to the equilibrium point. So, exponentially stability demands that the state trajectories converge exponentially fast towards the equilibrium point. So, the condition is like this: if there exists positive constants phi, k and lambda, such that if the initial conditions start within some region of radius c, then the trajectories x of t for all time are less than equal to an exponentially decaying function, where the rate of convergence is given by lambda, and this quantity is also dependent on the initial condition x of t naught. So, as we can see here, this term is not explicitly dependent on T naught, rather it is dependent on T minus T naught and x of T naught. So, what we can conclude from here is that exponential stability implies uniform exponential stability. So, we do not have, when we say the equilibrium point is exponentially stable, it implies that it is uniformly exponentially stable, because the definition itself is independent of the initial time T naught. Now, the next question is, does exponential stability imply uniform asymptotic stability? The answer is yes. So, in fact, it is a stronger notion of uniform stability. It also defines that the rate of convergence is exponential. The next question is the reverse: does uniform asymptotic stability imply exponential stability? So, the answer is no in general, because as I mentioned, asymptotic stability does not demand the rate of convergence. However, this relation is true in the case of linear systems, that is, uniform asymptotic stability of a linear system implies exponential stability of the linear system. All right, another very important notion in analyzing stability of nonlinear systems is local versus global stability. Now, for linear systems, stability is always global. However, for nonlinear systems, we need to talk about local stability. So, whatever notions of stability that we have done so far were all local. So, let us look at what global stability means. So, the origin is uniformly globally asymptotically stable, or in short we say it is UGAS, if all the conditions of uniform asymptotic stability that we discussed in the previous slide are satisfied for any initial state x of t naught. So, if we go back here, we stipulate that x of t naught start within some region of radius c. So, we say that this kind of stability is local, that is the initial conditions have to be within some local region of radius c. However, if we say that c is equal to infinity, that is the initial conditions can be chosen anywhere in the state space, we say that stability is global. Similarly, we have global exponential stability, that is if the condition of exponential stability is satisfied for any initial state in the state space, we say that the equilibrium point is globally exponentially stable. So, if we go back here, if we say that c is equal to infinity, that is the initial condition can be anything in the state space, and this condition is true, then the equilibrium point is going to be globally exponentially stable. As I mentioned, for linear time invariant systems, stability is always global. So, either they are globally stable, in fact they are globally exponentially stable, or they are marginally stable, or they are unstable. So, let us look at this example where I have a system with multiple equilibrium points. So, we can see here that this equilibrium point is a stable equilibrium point, that is if we perturb the ball slightly from its equilibrium position, it will eventually stay within the vicinity of the equilibrium point. However, here if we disturb the ball from its equilibrium position, it will not stay within the vicinity of the equilibrium point. So, this equilibrium point is unstable. If I ask you the question about the stable equilibrium point, whether this is local or global stability, then the answer here would be local stability, because I just mentioned that for global stability the initial condition, the initial state can be anywhere in the state space, and it will eventually stay within the neighborhood of the equilibrium point. However, if the initial state here is chosen to be the unstable equilibrium position, then it will just stay there for all time. So, this equilibrium point which is stable is only locally stable. Okay. So, the stability definitions that we discussed thus far are very rigorous. However, they as you can see, they are very hard to verify, because it requires that you solve the nonlinear differential equations, which is not a straightforward task. For linear systems, it is easy, because you could solve the linear systems and you could comment on stability. However, for nonlinear systems in general, it is not straightforward to solve nonlinear differential equations, and so the stability definitions that we discussed are hard to verify. So, Lyapunov theorems are useful in this scenario, because they help us determine stability without solving these nonlinear ordinary differential equation, and that is the real power of these Lyapunov theorems. So, Lyapunov proposed two methods. One is the indirect method, which is given a nonlinear system, you could linearize the nonlinear dynamics about the equilibrium point. However, you could only, and then so what we do here is that given any nonlinear system, we use the Taylor series expansion about the equilibrium point, and we get a Jacobian matrix. Then we can check the eigenvalues of the Jacobian matrix. If they lie on the open left half plane, we say the system is locally asymptotically stable. If they lie, if any of the eigenvalues lie on the lies on the right hand plane, we say that the system is unstable. However, if any of the eigenvalues has a real part which is 0, that is the any of the eigenvalues lies on the imaginary axis, we cannot conclude. So, although this method is useful because it takes you to the linear region, and then you could look at the eigenvalues, but it is inconclusive for certain cases, and so the Lyapunov's direct method is a more general method for determining stability. So, the basic idea is that it is based on generalization of energy concepts. So, it involves finding a positive definite energy like function, say v of t comma x, where t is the time and x is the state. So, it involves finding a positive energy like function. So, why do I say energy like? Because in certain situations it is easy to find the total energy of the system. For example, for mechanical systems you could find the potential and mechanical energy. Similarly, for electrical circuits it is easy to evaluate the energy of the system, but for many systems the notion of energy is not very clear. However, we could still come up with a positive definite function of the states, and we call that as the energy like function. And further, if the time rate of change of this v of t comma x is non positive, we say that the equilibrium point is stable. So, that is the basic idea. It is similar to the notion of the energy of of a system which is continuously dissipated, and if a system dissipates energy continuously, it will eventually settle close to the equilibrium point. So, this method gives sufficient conditions for stability, and it also talks about local as well as global stability. So, it is a very general method. So, let us look at the main theorem, which is theorem 4.8 in the book by Khalil. So, I encourage that you look at this theorem in more detail. So, this theorem says that we let us consider x equal to 0 to be the equilibrium point of the system. So, this can be said without loss of generality, as I mentioned before, and let us consider let there be a function v which is defined like this, where D is a domain containing the origin, and this function is continuously differentiable and it satisfies these relations. So, the first relation says that v of t comma x is upper and lower bounded by time invariant positive definite functions w 1 of x and w 2 of x. Okay. So, what this relation means is that v of t comma x is positive definite. So, if we can find a lower bound of this time varying function v of t comma x, and this lower bound is positive definite, then we say that this function v is positive definite. So, when is w 1 positive definite? So, w 1 of x is positive definite when w 1 of 0 is 0 and w 1 of x is greater than 0 when x is not equal to 0. So, this is what is meant by positive definiteness. The second condition, where v of t comma x is upper bounded by a positive definite function w 2 of x, this just implies that v of t comma x is decrescent. Okay, so, the first condition basically states that the function v is both positive definite and decrescent. Okay. So, let us move on to the second condition. So, the second condition is slightly more involved. However, if we look at it more closely, this is simply the derivative, the time derivative of v. So, v dot of t comma x can be computed by using the chain rule. So, we first take the partial of v with respect to t, and then we take the partial of v with respect to x times x dot, which is same as saying, so we replace x dot by f of t comma x. So, in a way we take the derivative along the system trajectories. The fact that we substitute for x dot using the function f, we say that this is the time derivative of the function v along the system trajectories. So, if the time derivative of v is less than equal to 0 for all t greater than equal to 0 and for all x on d, we say that the equilibrium point is uniformly stable. Okay. So, the definition that we had discussed previously, which was very hard to verify, can now be verified by using this Lyapunov's theorem. So, what this theorem essentially says is that if you could find a function v which is positive definite and decrescent, and its time derivative is less than or equal to 0, which in a way means that v dot is negative semi definite, then the equilibrium point is uniformly stable. So, suppose this condition of decrescence was not true, then we could only say that the equilibrium point is stable. The uniformity part is coming from the condition that the Lyapunov function candidate is decrescent. Okay, so, the second important theorem is theorem 4.9 in Khalil, which says which is very similar to the previous condition. So, this just means that v of t comma x is positive definite. This means that v of t comma x is decrescent, and this condition implies that v dot is less than or equal to minus w3 of x. So, w3 is a positive definite function. So, minus w3 is a negative definite function, which means that v dot is less than or equal to some negative definite function, which just implies that v dot is negative definite. So, if these conditions are true, the equilibrium point is said to be uniformly asymptotically stable. So, for asymptotic stability, we see that we have a stricter condition for v dot. In the previous case, v dot was only required to be negative semi definite. In this case, v dot is required to be negative definite. So, then we look at the last condition. That means, if this domain D is the entire state space and the function W1 is radially unbounded, then the equilibrium point is uniformly globally asymptotically stable. So, the fact that W1 is radially unbounded and the domain D is the entire state space suggests that we could include the notion of global stability here along with UAS. So, what does radial unboundedness mean? It just means that W1 of x goes to infinity for all norm of x tending to infinity. So, this is what we mean by radial unboundedness. So, as you can see here, we have not solved any nonlinear differential equation, but we have been able to comment on the stability properties of nonlinear systems. So, this is a very powerful condition. However, the main challenge here is to find the function v. So, how to find this Lyapunov function v to comment on stability properties is a perennial challenge in this area, and by intuition, by experience, by some trial and error, we could choose suitable Lyapunov function candidates, not just to analyze stability, but also we will see later to design controllers. Okay, so, some more remarks about Lyapunov stability theorems. So, the first one is that these are sufficient conditions for stability. So, they are not necessary, they are only sufficient, which means that failure of a Lyapunov function to satisfy the theorem does not mean that the equilibrium point is unstable. So, if you choose a Lyapunov function candidate, that is, you could find a function v of t comma x which is positive definite and its time derivative is at least negative semi definite, then we could say that the equilibrium point is stable. However, if the Lyapunov function candidate does not satisfy the negative semi definiteness of v dot, we cannot say that the equilibrium point is unstable, because these are only sufficient conditions for stability. So, you could find another Lyapunov function which may satisfy all these conditions. For linear systems, Lyapunov theorem provide both necessary and sufficient conditions for stability, and as I mentioned, finding a Lyapunov function for a nonlinear system is typically a non-trivial task. Okay, so let us consider some examples. So, let us consider this scalar system given by this nonlinear differential equation, which is also time varying, which means that this is a non-autonomous system, and we have been asked to analyze the stability of the equilibrium point. Okay. So, the first step is to determine the equilibrium points. So, for this we substitute the right hand side of this differential equation to be equal to 0, and we see that if this equation is true for any value of x for all time t greater than equal to 0, and we find that yes, it is indeed true when x is equal to 0. So, we say that x equal to 0 is the equilibrium point in this case. Second, we choose a Lyapunov function candidate. So, we choose a function which is positive definite. So, here we have chosen a very simple positive definite function x square over 2. Now, choosing this function requires some trial and error, some experience, and we will get better at it with time. So, let us just right now assume that we choose this as a Lyapunov function candidate, and let us see if this satisfies any of the conditions that we laid out in the theorems. Okay, so this function is positive definite, right. This function is also decrescent, because here W1 and W2 are simply equal to the Lyapunov function candidate itself. So, it is easy in this case because we have chosen a function which is not time varying. Next, we okay, just one more thing. So, this function is also radially unbounded. So, it is radially unbounded, positive definite and decrescent. So, we take the time derivative of v along the system trajectories, that is we differentiate it with respect to time and using the chain rule, and then we substitute for the system dynamics x dot equals this right hand side, and what we get is this as the v dot. We see here that we have this time dependence in v dot. So, v dot is in fact dependent on time, although v was not time varying. Now, this expression can be upper bounded by minus x to the power 4. So, can we conclude anything from here? So, as we said, we have been able to choose a Lyapunov function candidate which is positive definite, radially unbounded and decrescent. Further, we have also been able to find a W3 which is positive definite, that is we can invoke theorem 4.9 and conclude that the origin is in fact uniformly globally asymptotically stable. Let us move to the next example. So, this is a system with two states x1 and x2, and again we can see that this is a non-autonomous system. And we have been asked to analyze the stability of the equilibrium point. So, as we did before, we determine the equilibrium point, we set the right hand side to be equal to 0, and we find that x1 equal to x2 equal to 0, which is the origin, is the equilibrium point. So, next up we choose a Lyapunov function candidate. So, we try to choose a positive definite function. So, let us choose this as our Lyapunov function candidate, and how we choose this is we can talk about that later, but right now let us just go ahead with this choice. So, as you can see here, as opposed to last time, this Lyapunov function is in fact time varying. Okay. So, you could try different Lyapunov function candidates and eventually converge on a Lyapunov function candidate, which helps you to conclude about stability. So, we say here that this function v can be upper and lower bounded by time invariant positive definite functions. So, this is W1, this is W2. So, which means that v of t comma x is positive definite, and this suggests that it is decrescent. Further, since W1 is radially unbounded, we can conclude that v is also radially unbounded. So, next we take the time derivative of v along the system trajectory. So, we do the same thing, we take the time derivative, substitute the dynamics, and what we get is so we get some time dependence here, then we further upper bound the system like this, and then using some manipulations we convert it to this, and this we so this is a negative term. So, we just throw it out and further upper bound this by this expression. So, this expression says that v dot is negative definite. So, we have been able to choose a Lyapunov function candidate, which is positive definite, decrescent, and radially unbounded, and v dot is negative definite. So, we can invoke theorem 4.9 to prove that origin is uniformly globally asymptotically stable. Further, in this case you could also prove that v dot is less than equal to minus half v of t comma x. So, maybe you can try this as an exercise. So, with this you can in fact say that the equilibrium point is globally exponentially stable. So, wherever we can get this, we can say that v of t is less than equal to some exponentially decaying term, and since v is dependent on x1 and x2, we could potentially make similar conclusions about x1 and x2. Okay, so we move on. Okay, so the next thing that I wanted to discuss was signal norms. So, given any time varying signal, how do we find the size of the signal? So, these norms give us a measure of the size of any signal. So, let us talk about the LP norm of the signal x of t, which is piecewise continuous. So, the LP norm is defined like this. So, here p is any number from 1 to infinity, where infinity is not included. So, it is defined as this integral from 0 to infinity of the absolute value of x raised to the power p, and then you take, for the whole you take the pth root of this. So, we say that the function, the signal x of t belongs to the space LP if its LP norm exists, that is, that this integral is finite. So, this LP is a space of all piecewise continuous functions for which the LP norm is finite. Let us look at L2 norm. So, we just substitute 2 in P, and we get this P2 norm of the signal x of t. So, it is defined similarly. So, we say that x of t is L2 if the L2 norm exists, that is, that this integral is finite. So, this is a space of square integrable functions. Now, in this definition we of LP norm, we said that P cannot be infinity, because L infinity norm of the signal is defined slightly differently. It is defined like this, as a supremum over all t of the absolute value of x of t. So, we say that the signal belongs to the L infinity space if the L infinity norm exists, and that just means that the signal is essentially bounded. So, L infinity is a space of all bounded functions. So, this will be useful when we do analysis in this course. Okay. The other concept I wanted to talk about was asymptotic properties of signals. So, we say that so there are certain misconceptions about the asymptotic properties of signals. The first one being that if there exists a function f which converges to a constant c, that does not imply that its derivative converges to 0. So, as an example, you can consider this and try and prove that this is in fact a misconception. And secondly, we can also look at the reverse, which is if the derivative of signal converges to 0, that does not imply that the function itself converges to some constant. Example, we can take this function to be log of t and verify that this is the case. All right. So, a very important result that we will be using again and again in this course is the Bartlett's lemma. So, what the Bartlett's lemma says, so here in fact I am talking about the corollary of the Bartlett's lemma. So, if the function f of t belongs to L2 and L infinity, so it is both L2 and L infinity, it is both bounded as well as square integrable, and the function f of t is also uniformly continuous. Now, uniform continuity is a stronger form of continuity. So, without going into the actual definition of uniform continuity, what I want to tell is that it is sufficient to say that if the derivative of the function is bounded, that just implies that f of t is uniformly continuous. So, it is just sufficient to say this, that the derivative is bounded. So, if the function f is uniformly continuous, then we can say that as t tends to infinity, this function goes to 0. Okay, so, these three conditions have to hold, that is, the function has to be absolutely square integrable, bounded, and uniformly continuous. Then as t tends to infinity, this function converges to 0. All right. So, let us consider another example. So, here we have a system consisting of two states E and theta, and omega is given to be bounded, and we have to analyze the stability of the equilibrium point. Okay. So, the first step is always to find the equilibrium points. So, we set the right hand side to be equal to to 0, and we say that E equal to 0 and theta equal to 0 satisfies this equation for all time. So, this is the equilibrium point, and we have to analyze the stability with respect to this equilibrium point. So, let us choose a Lyapunov function candidate. V of as half E square plus half theta square. So, this is the most commonly used Lyapunov function candidate, the sum of squares. It is positive definite, it is decrescent, it is radially unbounded. So, it satisfies all the nice properties. Let us differentiate this. So, V dot is equal to E times E dot plus theta times theta dot, which is equal to E times, we substitute the dynamics. So, we see that these two terms cancel out and we are left with minus E square. So, what can we conclude about V dot? So, V dot is only negative semi definite. So, why not negative definite? Maybe you can take that as an exercise. So, V is positive definite, decrescent, radially unbounded, and V dot comes out to be negative semi definite. So, we can invoke theorem 4.8 in Khalil to conclude that the equilibrium point is uniformly globally stable. It is U G S. Okay. So, can we say anything more? So, it turns out that that we can. So, let us look at the signals, the signal E of t, and let us see if we can use any of our theorems or lemmas that we had discussed. So, here V is positive and V dot is less than equal to 0, which implies that V of t is bounded. Okay. So, since V is bounded and V is sum of squares of the states E and theta, that just implies that E of t and theta of t are also bounded. Okay. So, let us look at the equation. So, V dot equals minus E square. So, let us integrate this equation both sides from 0 to t. So, what we get is V of t minus V of 0 is equal to minus 0 to t of E square. So, we have already proved that V of t is bounded and this is some finite number. So, that means the left hand side is bounded, which means that the right hand side should also be bounded. So, this quantity E square should be less than infinity, which means that E of t is square integrable. So far we have concluded that E of t belongs to L infinity and it belongs to L 2. So, it is both bounded and square integrable. The only condition that we need to prove for E to go to 0 is that if E is uniformly continuous. So, to do that we will have to look at E dot. I mentioned before that if we can prove that E dot is bounded, that implies that E of t is uniformly continuous. So, we go back and see what E dot is. So, we look at E dot. So, E dot is minus E plus theta omega t. So, from here we know that E we have already proved as bounded, theta also we have proved to be bounded, omega is given to be bounded, which means that E dot of t is also bounded. So, we have proved that E dot of t is bounded, which implies that E of t is uniformly continuous. So, we have satisfied all the conditions, that is E of t is uniform, is both L infinity and L 2, and E of t is uniformly continuous. So, using 1 and 2 and invoking the corollary of the Barbalet's lemma, we can conclude that E of t goes to 0 as t goes to infinity. So, using Lyapunov theorems, we could only prove that the system that the equilibrium point is uniformly globally stable. However, then we used another lemma called as the Barbalet's lemma to prove that the state E of t converges to 0. So, in this case, although we can prove that E of t goes to 0, we cannot prove, or at least in this scenario, it is not possible to guarantee that theta of t also converges to 0. So, that we cannot guarantee. So, the system cannot be guaranteed, at least we cannot prove that the system is asymptotically stable, although we have proved that this is uniformly globally stable, and one of the states, that is E of t, converges to 0. So, this system in fact is going to be very useful when we look at adaptive systems in general, and this will be like a benchmark example for the adaptive systems that we will study in this course. All right. So, just to summarize, in this lecture we discussed the preliminaries which are required to understand this course, that is the notion of Lyapunov stability, the different stability definitions, and then we also talked about the Lyapunov stability theorems, which enable us to determine stability without solving the nonlinear differential equations. And then towards the end we read Barbalet's lemma, which is a set of conditions that enable us to prove that certain signals converge to 0 as time goes to infinity. So, these will be useful for us as we go on. I encourage all of you to go back and read about all the topics that we have discussed in this course in detail. Thank you.